In this assignment, we want to begin investigating how we can move from average velocity to instantaneous velocity. Well, you've been doing average velocities all the way through your algebra studies. So first we have an example of an object in straight line motion, and we know its position function. So we often use the letter S for the position of a function at a given time. And here we know the domain is from 0 seconds to 10 seconds. But in question A, we want the average velocity over this time interval. So we simply want to find the elapsed distance. So where did it end up? That would be its position after 7 seconds. Minus where did it start? That would be its position at 2 seconds. So that would be the distance divided by the time. The elapsed time, of course, would be 5 seconds. So this numerator will be in feet and our denominator in seconds. And we simply plug in 7 seconds and 2 seconds. And here we'll come up with 9 feet per second. And that's the average velocity over this interval from 2 to 7. Well, we know this formula, by the way, is a parabola. And we won't be surprised to find out in the next problem. We're going to try to find out what happens at 4.5 seconds. Notice that 4.5 seconds is right in the middle of this interval. So our next question is, what could we do to get an instantaneous velocity? Well, we don't know how to do that. An instantaneous velocity is only at one point. And clearly what we saw here a second ago is that we need to find the elapsed distance between 2 points. Well, the trick we can use is to say, well, let's still choose 2 points, but let's choose 2 points that are very, very close together. So, for example, let's find out the position at 4.5001 seconds minus the position at 4.5. So if we choose values that are close enough, let's find out if we can get within 3 decimal points. So I'm going to square those using my calculator, do some arithmetic here. I come up with 9.0001, and that would be in feet per second. Do I know that this is close enough? Well, you might try a variety here. So I might try, and you might try to go 4.4999. You could try to go a little bit on the small side. But if we choose some values very close, so let me notice I added some more accuracy here. Let's do this with a calculator again. And we just come up with some more zeros. So I don't know if I'm counting my zeros accurately, but you can see that we're close enough to answer our question to 3 decimal places. Now, there's absolutely no reason why I went on that side. So for example, could you have done 4.4999 seconds minus, and I guess I should probably turn these around. How about 4.5 and 4.4999? So there's no particular way that you have to do this, as long as you get really 2 points that are very close together. So we can see that the instantaneous velocity, we think to 3 decimal places. Not precisely, but close enough. So to 3 decimal places, it is about 9 feet per second. All right, so an instantaneous velocity we don't know how to do yet, but we can cheat by finding 2 points that are so close together that it gives us an approximation of the instantaneous velocity. Now we have a problem because we don't have an algebraic formula. Here we know we've got a vertical motion problem. So Tom fires this rocket straight up, straight down. You guys know from your algebra and pre-calc studies that vertical motion, when we graph this as a function of time, so height as a function of time, that this is going to be a parabola. but our data points might not be perfectly measured. So in the real world, when we measure data, it might not perfectly fit this model, but we kind of know the idea of a vertical motion problem. So here our first question says, using the data we have available, how could we find the average velocity over the interval from 2 to 6 seconds? Well, that's easy enough because we've got the data we need. So the height at 6 seconds minus the height at 2 seconds gives us our elapsed distance, and 6 minus 2 gives us time. So the elapsed distance divided by the elapsed time gives us an average velocity. So let's plug in our values here. And if my calculations are right, so now that's not the speed the entire time, that's the average velocity. We know it might speed up, slow down, and so on. It looks like the object is still rising at that point, so we know that it's going fastest at the bottom and then gravity is slowing it down. So we know this is not always the velocity, that's the average velocity. All right, how could we approximate? We can't do this exactly, but we could approximate the instantaneous velocity at 9 seconds. Well, let's look at our graph. We can't do a velocity with only 1 point. We have to use 2 points. So I would have to use an interval on one side or the other. And unfortunately, 6 to 9 and 9 to 12 are equal. So should we use the interval from 6 to 9 seconds? Or should we use the interval from 9 to 12 seconds? I don't think there's a reason why one of those would be better than the other. So our average velocity, set it up here and then put in your values so that your readers know where you are finding these values. 10, 10 minus 960 over an elapsed 3 seconds. So that gives us 16 2/3 or 16.6 repeating feet per second. In this interval, let me slide this over so it's this interval. We want to take the height at 12 seconds minus the height at 9 seconds. And we'll have our negative. So now it appears the object is falling. So here we're going to come up with, let me just scroll a little here for some space. If I've put this into my calculator correctly, negative 80.3 repeating feet per second. So you could come up with two very different answers. So the problem is it's rising on one side and it's falling on the other. So how do I know its instantaneous velocity at 9 seconds? Well, clearly we do not. We don't know whether it's still rising or whether it's falling. So we know something interesting is happening between 6 seconds and 12 seconds. So how should I give the best answer? I don't know which of these is better, but I might say that averaging the two of those. So the average of both of those answers, you might say, would be better than either of them individually. So you're going to come up with your own argument here. The average of both of those answers would give us negative 31.83 repeating feet per second. All right, so now we're going to analyze a little bit. So you might think that answer is better than either of the two individual intervals. Well, what do we know then about when it reaches its maximum height? Well, we just answered a lot of that question. Here we know that it appears that we're still rising between 6 to 9 seconds, and then we're falling, but we don't know that 9 seconds is exactly the symmetrical vertex. So how do we know when? Let's look at this picture I made a minute ago. How do we know where the 9 seconds is? Well, let's look at the distance between these. So the 960 to 1010, there it's only covered 50 feet. and here from 1010 to 769. So it's covered a lot greater distance. So it's falling faster from 9 to 12. So I think we could say first that we know that the vertex, or the maximum height, by first glance happens, or occurs, we might say, occurs somewhere between 6 seconds and 12 seconds. But now when we think about these distances covered, remember it's slowing down till it reaches its maximum. So we don't know that 9 seconds is the maximum. I think that you can tell, though, that the vertex, if you think about the symmetry, the vertex must be between 6 seconds and 9 seconds due to the symmetry of the graph and the distances covered. So as gravity starts speeding it up on the way back down. Okay, but we don't know exactly where. And our next question to analyze is, over how many different intervals will the average velocity be equal to 0? Well, if it looks like it hasn't made any progress at all, so notice that if we happen to choose two heights, if we happen to choose a time interval where the heights were symmetrical, it would appear as if the rocket wasn't moving at all. So as long as we chose two heights that were directly across from each other, so there's an infinite number of intervals. So we could say, due to symmetry, the average velocity equals 0 over an infinite number of intervals, as long as you chose two times that were symmetrically placed around the vertex of the parabola. When is the instantaneous velocity equal to 0? Only once. That would be when the rocket hits its vertex. Once at the vertex or maximum height. All right, so let's proceed here. Galileo got us a little closer by measuring the acceleration due to gravity. So for our vertical motion problem, if we ignore air resistance, and assuming that we don't have some odd-shaped object with a lot of air resistance, we can use this for our position function for a falling object. If you choose to just do the falling, not the rising and falling, you could put negative. It's your choice here. All right, so our average velocity over this interval, so we would want to do the position at time 6 minus position at time 2, and the elapsed time. And how I would do this, by the way, on my TI-89, I would go to the Y editor and put in this function. And then on the home screen of my calculator, I would do this all as one statement, y1 of 6 minus y1 of 2 in parentheses divided by, and then in parentheses 6 minus 2, which of course you probably know is 4. So let your calculator do all of the work here, and we will come up with, let me pause to grab my calculator, 39.2 meters per second. And again, we know that that's not the constant velocity, that's the average velocity, because we know over that interval this object is just falling. All right, so accurate to 3 decimal places, how can we come up with an instantaneous at 4.5? Well, again, you're going to do the same idea that we did in the previous problem. We can't do an instantaneous velocity, but we can cheat and we can use 2 points that are so close to 4.5. So we could do a calculation like this. And of course we know the difference between those. And I'm going to pause the video to grab my calculator. All right, and I'm back. I have 44.1 meters per second. There's no reason, by the way, that we have to do that side. We could say, why don't we do S of 4.5 minus S of 4.4999. And again, the elapsed time would still be similar. And when we calculate, we should come up with something similar. And yes, I get 44.1. All right, so you have to come up with your answer to 3 decimal places. So let me add a couple zeros there. Make sure you put in those zeros since that's what we were asked to do. Sorry, my tablet wants to erase those. And some more from data. All right, so we are draining water out of a tank and we've got the velocity at various points. So on the graph of the velocity function, find the slope of the secant line joining these 2 points. Well, that's pretty easy. The slope of the secant point is simply y2 minus y1 over x2 minus x1, and that would be our slope of the secant. And I get negative 38.8, and our units here are y units, gallons, and our x units are in minutes. So we want to make sure we label these. What does this tell you? This is the average. This is the average rate of water flowing out over the interval from 10 seconds to 15 seconds. You don't have to keep putting that SEC, by the way. Just an S for seconds would be fine. All right. And now we want to do another problem over a different interval. So the slope of this secant, change in y, change in x, and I get negative 27.8 gallons per minute. So this is the average rate of water flowing out of the tank. Over this interval. And why is it different? Well, apparently in this problem, so when there's less water in the tub, it drains, the slower it drains. Less water, the slower it drains. Completely hypothetical, by the way. All right, and one more. Estimate the instantaneous, or the slope of the tangent, at the point 50 and 250, and can we use our answers in part A and B? Well, because those answers surround 15, we could use the symmetry, so we could take the average of the answers from B and C due to the symmetry of the time intervals. So the average of our previous two answers would give us negative 33.3 gallons per minute is an estimate or an approximation of the instantaneous rate of water flowing out of the tank at t equals 15 minutes. We don't know if it's a good answer, but using the data we were given, it's the best answer we can give.